In this segment, we're going to take curried functions and call them with too few arguments and see why that's a neat thing to do. So previously, we used currying just to simulate multiple arguments. If you wanted a 3-argument function, we used currying to have a function that returned a function that returned a function to have 3 arguments. But what if we took those same function definitions and as callers just passed in fewer arguments, 1 or 2 instead of 3? Well, then what we would get back is a closure that's waiting, if you will, for the remaining arguments. There's no new semantics here. It's just a pleasant idiom that is completely allowed. You can always call a function that returns another function and then save that function and have it around for when you want to call it. So this is called partial application. It's very convenient and useful. You can do it with any curried function, and I'm not showing you any new language constructs here. So let's do a couple examples. I've already written out all the code for this segment. So we have our 2 curried functions from the previous segment. We have sorted 3, which takes x, y, and z curried, and fold, which takes f, ac, and x's curried. And now let's notice that we could just call sorted 3 with 2 arguments instead of 3. So we're going to call sorted 3 with 0. That will give back a function. We'll call that with 0. We'll get back another function. And when we call that function, what we'll end up doing is taking in an argument z and asking, is z greater than or equal to 0? And is 0 greater than or equal to 0? So fundamentally, what we got back was a function that takes in 1 argument and tells you if it's non-negative. Well, that's not the most useful function in the world, but how about something actually useful, like summing up all the elements in a list? Here, I have a call to fold, where I've also passed in 2 arguments instead of 3. So what I'm going to do is get back a function that expects a list x's, right? It'll basically be this function here, and we'll fold over it using this for f in its environment and this for the initial accumulator. So this will actually sum all the elements in the list. Now there are other ways, perhaps more intuitive to you before you've seen this technique, ways to write these functions. I could write is non-negative by just being a function that takes in x and calls sorted 3 with 0 and 0 and x, or sum all the elements of the list the same way I showed you in the previous segment, where we just create a function that takes in x's and calls fold with these 3 arguments. It's just longer, right? These are pleasant. We get used to it. It's a convenient thing, partial application. These are not terrible. This is not awful style. But we want you to get some practice with the shorter way that demonstrates that you understand how currying and partial application work. And in fact, if I go back to the slides here quickly, the reason why this second version is really the same as the first version is actually something we've seen before, just a little bit different. This top version is just unnecessary function wrapping, right? We have seen before that we shouldn't write fun fx equals g of x when we can just write val f equals g. Well, it's the same thing here, except instead of just having a variable g for the name of the function, we have the function that you get by calling fold with this anonymous function and 0. All right? So let me show you a couple more examples I have here of just currying and partial application being useful to hopefully get the hang of it. Here's a function range, which takes 2 arguments in a curried form. And essentially, if you call range with something like 3 comma, not comma, we're not tupling, range 3, 6, that produces the list 3, 4, 5, 6, something like that. All right? And so if you call range with just 1 number, like say 1, that's going to give a function back that when you call it with a number, returns from the 1 up to that number. And so count up of 6 would return the list 1, 2, 3, 4, 5, 6. All right, just another example where we didn't need this unnecessary function wrapping version that you have here. The function range 1 is a perfectly good function. We can just say val countup equals range 1. As a more useful example, our iterators, our higher order functions over lists and data structures like that, are often written in a curried form. So let me show you another example just to sneak in another useful iterator. Here's a higher order function exists, that takes a function, which I'll call predicate, and a list x's, and returns true if there exists an element of the list for which predicate returns true. Otherwise, it returns false. So this is a simple 3-line function. The empty list should return false. There does not exist an element of the list for which predicate is true. Otherwise, it's predicate applied to the first element of the list, or there exists some element in the rest of the list for which predicate returns true. So that's exists. Here's a use of it. If you call exists with a function that checks whether its argument is 7 and a list that does not have 7, you'll get false. All right, so that's the result here, is false. But much more interesting is to take exists and partially apply it. If we apply it to one argument, we'll get back a function that takes a list and returns a bool. So has 0 does indeed have type int list arrow bool. And when you call has 0 with an int list, it will check whether any of the elements in the list are 0. Because exists with this anonymous function returns a function, returns a closure that, given a list, checks what we want to check. Similarly, the built-in library functions in the list library provided by ML standard library are often written in curried form. So list.map is actually defined for us, but it's curried. So if you call it with fun x arrow x plus 1, you get back a function int list arrow int list that will indeed add 1 to all the elements in the list, returning a new list. And list.filter works the same way in the standard library. If I call it with this function, I will get back a list that is also an int list arrow int list is the type of remove zeros, and the list I get back will have all the zeros removed from it. So that's very elegant, and when you go to use these functions, you have to use them in a curried form. Here we're using partial application. But there is one thing that I don't want to talk about right now, but unfortunately I have to. So once you start using these polymorphic curried functions with partial application, you might run into this thing called the value restriction. The value restriction is something that's in ML for very good reasons. The type system would be broken without it. But I don't really want to talk about it right now because it's confusing. But you may see something about warning type vars not generalized. And if you see that warning about some partial application that you have, you're not going to be able to use the function you get back. And this should surprise you. You have not actually done anything wrong in terms of what I have taught you so far, but you simply have to work around it. And no language is perfect. This is an ugly fact of life in languages like ML. So let me show you an example of what might happen. Use partial application all that you want for now. It's a beautiful idiom. But if you do something like this, where the result would be a polymorphic function. So I'm going to map this across something. So this could take the resulting function could take any kind of list and would return an alpha star int list of the same length, where I put a 1 next to every element of the list. And this will give that weird warning. And it won't be able to be called, and how should you work around this? Well, the first way is to just give up on the partial application and put in what I said was unnecessary function wrapping, but now is a little more necessary. If you don't like that, and you really want to do partial application, then you can put in an explicit type that's not polymorphic, like this, and then you have a perfectly fine function, but it can only be used with string lists, not with any kind of list. I should also point out that on homework 3 and things like that, you are not likely to run across this, because it only happens when the resulting function would be polymorphic. So for example, this call will not give any kind of warning, because we can tell from this anonymous function that it can only be applied to int lists anyway. So just wanted to talk about that. Didn't really want to, but in case you hit the warning, I didn't want a bunch of questions of that thing you taught me to do isn't actually working. It usually works. When you get the value restriction for things like list.map, I've given you a couple of workarounds.